Welcome to Earth Science, everybody. So, if you're following the survival guide, and I know we're early in the year, you should have already done this part right here. You should have a couple notes written down. Quick, jot down a couple of things in Cami. Let me know what you saw as a difference between those two beakers, and we're going to come back to that and come back to it, like I said. Let's start to get down some of the basic ideas of density, though. And this is like an old, kind of silly trick question that somebody will, is like a dead joke trick question. Somebody will ask you at some point in your life, what weighs more, a pound of feathers or a pound of bricks? Now, sometimes people get the urge to say, well, bricks, because bricks, like, they weigh more, right? But what you got to pay attention to is that they're asking a pound of feathers versus a pound of bricks. So they are equal. They weigh like 1 pound is 1 pound. Doesn't matter what it is. Bricks, feathers, Legos, whatever it may be, right? So if you were thinking bricks, if that was the thing that popped into your head, you weren't thinking about weight. What were you really thinking about? You were thinking about like their heft. How heavy do they feel? And that's really what we're getting at today. This is the whole thing. We're going to be talking about density. That's what you were thinking. I'm going to make that nice and big. Okay? In that regard, if you had to break a car window for some reason, which I don't advise you do unless it's an emergency for some reason, what would work better if they were all about equal size? A baseball, a tennis ball, or a rock? All right. What do you think? Yes, it's the rock. Now, if you're thinking, well, yeah, because the tennis ball is like squishy and it will just bounce. That's not where we're going. Keep in mind, this is where we're at. We're thinking about density. If I took this tennis ball and just somehow made it hard, froze it to a ridiculously cold temperature, I don't know, whatever, put a candy shell on the outside and made it hard, it's still not necessarily going to be enough to break the window. If you feel a tennis ball, it's pretty light, right? Yeah, baseball's closer, a little heavier, but a nice rock that's been bouncing around on the beach very hard, that's going to be your choice. And again, why? It's not how hard it is. It is the most dense. All right. So the reason I'm going through this kind of slowly and deliberately is this idea of density is maybe what you're used to in terms of the heft of something. Okay. How like chunky, heavy does it feel given its size? All right. So let's think about these boxes with the size of the spheres inside there representing like matter, like stuff here in this universe. If each box has about the same amount of space, well, which box has more of this matter in it or more of this mass in it? Well, it's this one over here on the right. I'm going to go back down to normal font here. The one on the right over there. So therefore, which has the most density? Well, what density is how much stuff is in there relative to the volume. If I took this rock at that mass, take that weight, but made it the size of a car, it would actually feel pretty light if you had to somehow try to pick that up. Right? So how much mass is in it compared to how big it is? That's the idea of density, really, of heft, of heaviness. This has more stuff packed into a volume. This tennis ball has less stuff packed into a volume. So this feels heavier to us. And what we really should get in the habit of saying is that it feels more dense. This feels less dense. That's somewhere in the middle. Okay, so the higher density, same thing on the right. All right. So comparing different densities with each other, objects, I'll switch colors here. Let's go blue. Objects with higher density means more mass per volume, more stuff packed into that amount of space, will, if you got to compare two things, and this is why we do density early in the year because it comes up over and over and over again. When we talk about cold air coming down from Canada or warm air coming up from the Gulf of Mexico, those are two different density air masses. And what happens when they hit each other? We got a long time to figure that out, but we got to understand what happens with density first. Inside the Earth, the way that magma might churn around has to do with temperature and density. So dense stuff does what? Less dense stuff does what? In ocean currents, this like shows up over and over and over again in universes, all of that. So if you have a higher density, all things being equal, they will tend to sink and feel to you heavy. Whereas objects with less density means less mass per volume and floats and feel light. Many times in class, I've asked students, why do hot air balloons rise? And there's always people that like go, oh, they fill them with helium. No, they don't. And by hot air balloon, you know what I mean? Those ones that are like a giant balloon with a basket that you can send 3-4 people up into. They don't fill those with helium. They fill them with hot air. They're called hot air balloons. So why do they rise? Well, that hot air tends to be less dense than cold air. And if it's less dense, it's going to float. So it just floats due to that density, that less density, less dense air inside the balloon versus the more dense air outside the balloon. Okay, so again, when we talk about cold air coming down from Canada, warm air coming up from the south, when they hit, which one rises, which one sinks? It's all about this density. Okay. All right. We're getting there. So time to think. Like, what happens if I take a rock? All right, here's one right here. If I take this rock, it's got a mass, I could put it on a balance, figure it out. It's got a volume, I could figure that out. I could divide those and get the density. We'll be doing that down here. Don't worry, your time's coming. So this has a density, right? What happens if I took this rock and I broke it in half, if I had much stronger hands? Well, the mass would decrease. If I had one piece, instead of, if I took this, threw the other one out the window, and I'm left with half of it, it's now got less mass. The other half is gone. The volume, well, half of it's gone again, so the volume decreases. What happens to density? In fact, if I could mathematically break it exactly in half with magically strong hands, I'd have half the mass, I'd have half the volume. But what happens to density? But if you're really getting density as like the idea that it's how hefty the molecules are in a given volume. If I break it in half, I don't really change anything about that. I decrease the mass, yes. I decrease the volume, but the ratio of those two to each other, which is what density is, which is what this idea of heftiness is, stays the same. So this is like a really important rule. It might come up over and over again and is the key if you're stumped when we're doing these questions. What two substances could be made of the same material? It's the key to that question. If you've got two pieces, you don't do anything to the density. Changing size does not change density. So that's why we can say things like so galena, which is what this mineral is, and we don't have to worry about rocks till the third Markan period. But hey, let's take a quick sneak peek at your earth science reference tables. Galena's density is 7.6 grams per cubic centimeter. They can say that about this piece in my classroom. New York State and Albany can put these reference tables, and they know that this Finnerty guy in Pulaski has a chunk of this in his drawer, and its density is 7.6. And they know that because the size of this doesn't have any effect on the density. It's what is inside of there. It's this lead and sulfur that make this mineral up that determine its density. How closely packed are they? How do they fit in with each other? It's standard. It's the same as the piece of galena that they have in Sandy Creek schools and the same as the piece of galena they have in Buffalo, Albany, Rochester, wherever, right? Everywhere in the world, galena has this density. Okay, I forgot what it was. 7.6. We're at not that this, you don't have to memorize this by any stretch of the imagination. Grams per liter. The other one's like cubic centimeters. Don't worry about that. We'll teach you that trick later. Right, so take something, break it in half. The density of each half stays the same. Yes, it's smaller. Yes, it weighs less. But the density is the same. You didn't do anything to change the molecules. All right, so that's a big one. That's why I put these blue stars there. Let's use our head again. If I break an object in two, the density is the same. Granted, we know that. But what if I smush it? What if I compress it? So usually I use a balloon, and I couldn't find one this year, so I'm using, it's a balloon. I mean, it's a balloon, right? It's a balloon. I'm using this balloon. If I took this balloon, which has a mass, again, I could put it on a balance, figure it out. It has a volume. It's taking up this much space in the universe. Okay? Therefore, it has a density. It is pretty light. It's not very dense, but it has a number that we could assign for its density. But what would happen if I, hopefully don't pop it in this, but smush it into a smaller amount of space? Have I changed the mass? No. It still has the same mass. Have I changed the volume when I do that? Yeah. I'm crunching it into a smaller amount of space. I'm decreasing the volume. So if I smush it, compress it is like really what I should say, right? But the molecules get closer together. So, and that idea of this box right here, I'm taking it, or maybe it's like this, and I'm mashing all those things closer together. I'm getting something that's more dense. The density increases. The principle is essentially the same. You've done this experiment. I'm going to say that a lot this year. You've already done this earth science experiment. If you've gone out in this region, especially, I'd be willing to bet everybody's done this, and thrown a snowball. All right, so you go out there, you're young, you scoop up some snow, and you chuck it, and it just kind of like powder flings all over. It doesn't do anything, right? So what your scientific brain says, this earth science experiment that you've like innately done, is, hey, if I take a larger volume of snow, go like this, and smush it into a smaller amount of volume, I'm increasing the density of the snow such that it sticks together in a ball, and I can chuck it and try to make my kid brother cry, something like that, right? That's what that's this equation that we've got to figure out. You said, okay, a mass of snow that if I just pick it up and throw it doesn't do anything, but if I take that mass of snow, put it into a smaller volume, I increase the density. You've done it, and you can keep on doing it. So what I'm going to do, I'm going to stop this video. There's going to be a new link right here for this part, right where it says L, where we'll deal with the math of it, which is going to get, a little bit of algebra, but you guys are going to do great. But let's pause and have you think about some of the concepts. I would like you to fill out 1 through 5 before starting this. Once you see some answers here, and I'll be pulling these up online as you work on them and thinking about any edits if we need to. But I think you're going to do a great job. Okay, so check those out using those ideas, and then we'll tune in later, look at the survival guide, and finish this guy out. All right, thanks for tuning in, everybody. Welcome to the new year. Welcome to Earth Science. We'll talk to you soon.